Hello and welcome to another session of HCI 509, Research Methods and Statistical Analysis. In this lecture, we'll talk about significance tests. Let's get started. So significance tests are going to be a foundation for how we determine whether to reject or accept the null hypothesis. So why do we need it? Well, consider the following statement. Mike's height is 6 foot 2 inches. Mary's height is 5 foot 8 inches. So Mike is taller than Mary, right? Well, the targets being compared are the heights of two individuals. And these are both known numbers. We can measure them. Another person could come 10 days later and measure them. Their heights are not going to change much. And it's easy for an independent evaluator to come and do this assessment and always come up with the same conclusion. Based on these two numbers, we know that Mike is taller than Mary. So why do we even bother to need statistical significance? Let's consider another set of statements. So the average height of three males, Mike, John, and Ted, is 5 foot 5 inches. The average height of three females, Mary, Rose, and Jessica, is 5 foot 10 inches. So our conclusion based on this is that females are taller than males. What's wrong with this statement? So here's a couple of common responses that you might hear if you made this proposal that females are taller than men and you ran this by some other researchers. Well, by common sense, I know that males are generally taller than females. So what you're hearing is that people's observations of the general population are different than what you've seen in your sample. Another might be, I can easily find three other males and three other females in which the average height of the three males is taller than that of the three females. And another might be, there are only three individuals in each group. The sizes of the comparison groups are too small. The individuals in both the male group and the female group are not representative of the general population. What we need to do is we need to factor a distribution that you're going to hear several times in this course. And that is the normal, sometimes it's called the Gaussian distribution. So the claim that females are taller than males is wrong due to inappropriate sampling. Remember, the first statement compared two individuals, so that is pretty much indisputable. But the second one was more general. It stated that females are taller than males. And this requires us to have a population, in this case, all females, all males. And then the sample were the three males and three females that we brought and did our experiment on. The problem here is that the population and the sample are different. So the distribution of heights of the human population and many other things follow a pattern called the normal distribution. And you've heard about this. It's used in grading. It's used in all sorts of things that are viewed as natural, like you have outliers and so forth. So the types of data sets can be illustrated by the bell-shaped curve, with the majority of the data points falling within the central area surrounding the mean of population, which we call mu. So in the graphic you see up in the upper right, you see the mu is going through the top of the bell, and then you have A and B. And A and B might represent the different heights of two sets of individuals in your sample, and this allows us to make that comparison. The further a value is from the population mean, or mu, the fewer data points would fall within that area around the value. Sampling is an important aspect because if we don't sample correctly, this could lead to bias. Let's just say in that example that we talked about with the three males and the three females, the three females you happen to sample that were on the basketball team. And the males you happen to sample were in middle school. So Sure, they're males and they're females, but they're not representative of the overall population. When we compare two large populations, such as males and females, there's no way we can possibly collect the data from every individual in the population. We can come close, but it's neither reasonable for you as a researcher to gather all this information, nor is it expected. So we have to come up with a sampling technique that allows us to get a representative sample of that large population. So sampling is this process. It's selecting the smaller group from the large population and using it to represent the entire population. So the keyword here is represent because we want to make sure it represents the average, so the bell curve for the population and the bell curve for the sample should look identical. So in that example, we had 3 males and they happen to be shorter than the average females, but the 3 females happen to be taller than the average females. And this allowed us to conclude incorrectly that females are taller. Another thing that we need to consider are significance tests. This allows us to determine how confident we are that the results observed from the sampling population can be generalized to the entire population. So if we have a student's t-test or a t-test that is significant at the p less than 0.05, this we can use to say that we are confident that 95% of the time the test result correctly applies to the entire population. Let's just say we do this test 100 times. Each time we gather the same sample, not the same people, but the same sampling technique. And we run this test 100 times. And we grab males and females and look at the average height from these two groups. And in this case, we can conclude that the males are taller than the females. If, on the other hand, we concluded the other, so we basically had the hypothesis that females are taller than men, to get a significant test, we would have to have this repeated at least 95 out of 100 times, which we might be lucky once, we might be lucky twice, but to get this 95 times, assuming our sampling technique is correct, is going to be very difficult. If we want to look at this in technical terms, going off of what we've talked about so far, significance test is where we have a null hypothesis and we contrast that with an alternative hypothesis to determine the likelihood that the null hypothesis is true. What we do is the null hypothesis, remember, is the more conservative or status quo. And so that typically has the benefit of the doubt. Let's talk about it. So next we're going to look at errors and probability. To do so, we look at type 1 and type 2 errors. A type 1 error is also called an alpha error or a false positive. It refers to when we reject the null hypothesis when it's true and should not be rejected. A type 2 error is called a beta error or a false negative. And this refers to the mistake of not rejecting the null hypothesis when we actually should have. So let's take a look at some examples. In the US justice system, a defendant is presumed innocent until proven guilty, right? So we have the following null and alternative hypothesis. The null hypothesis is the defendant is innocent. So you can see here, this is the more conservative status quo. And then on the alternative, we say the defendant is guilty. So the type 1 error, if one was committed, remember this is the false positive, the jury decides that the defendant is guilty when he or she is actually innocent. So the null hypothesis, which is the defendant is innocent, is rejected when it's actually true. In other words, the defendant was innocent. The other is a type 2 error. And remember, this is where the jury decides the defendant is innocent when he or she is actually guilty. So the null hypothesis was accepted, meaning the defendant is considered innocent, when actually it should have been rejected and the alternative hypothesis accepted. So here's another example that ties more into HCI. These researchers go out and evaluate whether ATMs with a touchscreen are easier to use than ATMs with buttons. So the null hypothesis is there's no significant difference between the two. And the type 1 error in this case would be that the research team decides that the touchscreen ATMs are easier to use than ATMs with buttons, when actually there's no difference. The type 2 would be that the research team decides that touchscreen ATMs are no better than ATMs with buttons, and there's no difference, when actually touchscreen ATMs are better. So the consequences can have different types of, usually it's negative consequences. So in the last example, a type 1 error may lead the bank to spend money to switch to ATMs that are touchscreen, but they don't really provide any value to the customers. Whereas a type 2 error, the bank doesn't do anything. They just stay with the ATMs with buttons, and they lose the opportunity to make better value for each customer that uses its ATMs. So if we look at this, we have on the left-hand side, we have the reality. So this is the ground truth. And at the top, we have our conclusion. So this is what our study concludes. You can see there's check marks in the places where we get it right. And then we have type 1 and type 2 errors where, for example, for the type 1, it's where we say the touchscreen is easier when actually there's no difference. The type 2 is where we say there's no difference, but actually the touchscreen is easier to use. So here's a graphical example. Now this is one that is used quite often, so it's almost a meme. But in the top here, we can see we have true positive and true negative. So the doctor says to the lady who looks very pregnant, you're pregnant. Looks to the elder gentleman and says you're not pregnant. Okay, so that's what we would expect. So a false positive, which is a type 1 error, is when the doctor says to the elder gentleman that you're pregnant, when actually there's no visible chance that he's pregnant in this example. The other one would be a type 2 error, where we have a false negative. And this is where the doctor says to the pregnant lady that she's not pregnant. Which is worse? Well, so it's generally believed that type 1 errors are worse than type 2 errors. But let's consider a cancer study. Okay, so they have a cancer screening, and this is an initial screening. So if somebody goes through the process and it finds that they have cancer, the test will say, come back for a second test, a more comprehensive one. So in this case, let's just assume that the test comes back and it says that the person has this particular type of cancer when they actually don't. So that would be a type 1 error. In this case, the person's going to be really worried. They're going to call their friends, but they're going to go get that second screening and they're going to find out that they don't have cancer when they were initially scared thinking that they did. But let's consider the other. Let's consider a type 2 error. This is where the person's told that they don't have cancer when actually they do. So they don't go through the second screening. They end up getting more severe symptoms. They end up perhaps dying or being incapacitated. Doctor gets sued, the hospital gets sued. So in that case, a type 2 error is far worse than type 1 error. So it is context dependent, but for the general sense, it's believed that type 1 errors are actually worse than type 2. So type 1 errors say we actually make the condition worse than the current state. Remember that ATM example? This is where we actually make a change to the ATM buttons. We go to touchscreen instead of the buttons. And actually, this makes it worse. So the type 1 error could result in a worse condition. Another one that relates to medicine is if a new medication's found to be no more effective, they may switch to a less effective treatment. Type 2 errors can cost the opportunity to improve the current state. So a type 2 error means the test doesn't reveal that the new medication is more effective, so the patients miss this opportunity to actually get better treatment. So how might we mitigate the risks of these types of assessments? So let's talk about some nomenclature first. So alpha is the probability of making a type 1 error. So this would be the significance level of the p-value. Remember that 0.05? So what that means is the 0.05 refers to the 5 in 100 chance of making a type 1 error. So beta is the probability of making a type 2 error. So we say 1 minus beta is the probability of successfully rejecting a null hypothesis when it's false and should be rejected. So let's talk about how they interrelate. Under the same conditions, decreasing alpha reduces the chance of making type 1 errors. So instead of having a 5 in 100 chance, let's say we had a 1 in 100 chance of actually having a type 1 error committed. But this is going to increase because what we're doing is we're being more conservative, is we're going to increase the chance of making type 2 errors. So reducing the chance of making a type 1 error is going to increase the odds that we miss something that's actually true, meaning that our research is more vulnerable to type 2 errors. So how do we reduce these? Well, it's generally suggested that we use a large sample size. So when the effect size, meaning what is different between the two samples, is small, if we have a large sample size, we're able to detect that, and it has more, we have more emphasis because we have a large sample size. This gives more credence to the fact that what we observe in the difference is actually representative of the population. So let's talk about p-value. Again, from what we're learning here, it's generally believed that type 1 errors are worse than type 2 errors. So a very low p-value is adopted to control for the occurrence of type 1 errors. So this is, again, where we have a false positive. We want to make sure that the false positives occur rather rarely. If we return a value that's less than 0.05, it means that the probability of making a type 1 or false positive error is below that 0.05 or 5%. So the probability of mistakenly rejecting a null hypothesis is rather low, below 0.05 or 5%. I hope this has clarified the purpose and some important concepts behind significance testing. I hope you enjoyed the lecture. I'll see you next time.